Um, on number 5, we know how to do it, like the derivative over the original, but we just needed help taking the derivative.
Okay, this is e to the 0.3 t squared?
Yes.
Okay. So all we need to cover here is how to take this derivative?
Yeah.
All right. Well, why don't you get started on this, and if you get stuck, I'll show you how to get unstuck. So how would we get started here?
Okay, you start by just the original.
Mm-hmm.
And then you have to multiply by the derivative of what's in the exponent.
Oh, wait.
What? So would it be
Right?
Would it just be times
2
0.6
times
t?
0.3 t.
Okay. Let me check, but I think you're on the right track. The key here is to realize that this is a composite function. Again, you really have two functions. You have an exponentiation function. There's really two different functions here. On the outside, you're doing exponentiation. I just invented this, a new independent variable for that. And on the inside, this is the function that you're taking.
Okay.
So that should be outside prime times inside prime. Well, the derivative of e to the u is just e to the u. And the derivative of the inside would be 0.6t. And the last thing is that when you take the derivative of the outside, you evaluate it at the inside. So for u, I should plug in 0.3t squared. I think that's what you got.
Yeah.
Yeah.
What about a problem like page 324?
Oh, is it different pages?
Yeah, it's like way ahead, but
I probably have different pages. By the way, before I forget, let me just mention one other thing we did on that last elasticity problem. They were asking us for the elasticity when the price was $6.
yeah.
But remember, it was better to first get a general formula for elasticity and only then plug in the number 6 for P. Oftentimes that's important in calculus. First, even if they're asking you about when the variable is equal to a particular value, first get the general formula in terms of the variable and only later plug in. Because if you plug in the constant too soon, you can't take the derivatives.
Okay.
That's the same deal for this problem. This problem, they actually asked you for the derivative at, say, x equals 10, or t equals 10, but we didn't plug in the 10 at the start. First we took the derivative, and then we plug in the 10. So let me see what page you're looking at.
We'll do this one.
Yeah, we just do number 9 as well.
From that same page?
Yeah.
But I think,
Oh, and future value.
yeah. But now since we learned logarithmic derivatives, should we try it first? I don't know.
Yeah.
Number 9. Are you using a logarithm?
I'm finding the derivative.
So let's see. So the question is asking us for the percentage rate of growth. Now we know that oftentimes the best way to find percentage rate of growth is to take the derivative of the log. So we should take the log first before we find the derivative.
No, no, when you use your usually long exponents, maybe not.
So we have two different possible approaches for finding percentage growth. We can take the derivative of the original function over the level, or we can take the log of the function and take its derivative. And you should use, in general, whichever one looks like it's going to be more useful. Well, remember that what are logs good at simplifying? They're good at simplifying products and exponentiation. And here we got a lot of products and exponentiation.
And it tells them.
And they told us, that's right. But even if they hadn't told us, it's going to be much easier to use logs here because there's so much products and exponentiation. So the first thing we have to do is actually take these logs. And the log of the product is the sum of the logs. That's a good start. And then it looked like you did a good job simplifying this.
I got stuck simplifying that.
We know that taking a square root of something is the same as raising it to the 1/2 power. So I've replaced the square root with the 1/2 power. And you know the simplest thing to do now, how can I simplify this power further before I do anything about this? Why don't we take the 1/2 out in front?
Okay.
Because otherwise we're going to end up with exponents on top of exponents. Now it's going to start to confuse me.
Yeah. Okay, that's where I got confused.
So from the rules we saw previously, when we have an exponent inside a log, we can turn it into a coefficient in front of the log.
Okay.
We could have continued to simplify this, but that's just going to give us a confusion of exponents. So let's make this simplification first. And now we can simplify this.
ln of e is 1.
Well, actually, what did you say that you would do?
ln of e is 1.
Right, although, all right, so what did you end up with?
I didn't do it.
Times t
I didn't
to
do
the
it,
1/2.
yeah.
All right, so let's work it out on paper.
So 1/2. No,
T
sorry.
to
T to the 1/2.
Right, so technically, the first thing to do here is, now again, we can take the exponent out and make it into a coefficient. And only once we've done that, can we now take the logarithm of e.
Okay.
And you can see that taking the logs really did give us a nice simplification of what we started with here. Is this what you guys got?
Yeah,
That's right.
especially now. Okay, so now if we take the derivative, then that cancels. That becomes 0 again, and we're left with like a simpler derivative of t root t over 2.
Yeah, so let's figure out what that derivative is. What would be the derivative of this? Sounded like what you were saying was right.
Okay.
0.
Looks good.
And then we would plug in what they told us.
So as usual, we can turn the square root into a 1/2 exponent. And then we end up with this as the derivative. We might as well finish this off, so let's figure out what the answer is.
It's 1/8.
So we should plug in the number 4. On your calculator, you'd have to put the exponent in parentheses, and you get 0.125, or 1/8.